applications of supercapacitors, like for electric vehicles. I'll come in details later on. And the portable electronics, wearable devices, everywhere we can use the supercapacitor as a energy storage device. Now, supercapacitor. The supercapacitor means there are three main components of the supercapacitors are the electrode, electrolyte, and the current collector. Here in this image, you can see the electrode materials are the black dot. Those things are the electrode materials on the both side. Right, and the light blue is the current collector part. And in between, there is a separator between two electrodes. We use generally some paper-based separator if we use the aqueous electrolyte, or if we use the solid gel electrolyte, then we don't need any paper separator. And here the mechanism is when the charging is occurred, there are the electrolyte ions. The ions from the electrolyte store on the surface of the electrode materials, and the electronic charge stored on the electrode, and their separations becomes of the order of atomic level. So if the separation between positive and negative charge becomes of the atomic level. So we can see that we can say that the capacitance value will be really high. Whereas the electrode material we use is not like a plate capacitor plate, metallic plate. If these materials are porous material we use, so the effective surface area, that is the specific surface area, is really high. That also will increase the capacitance. In this way, we can increase the capacitance, and we can get the. When I say the 1000 farad per gram means is a specific capacitance. When we use 1 gram of material, it gives 1000 farad of capacitance. Okay. So the supercapacitors actually mainly two types of supercapacitors. There are electric double layer capacitors. Mainly we use the activated carbons, carbon nanotube, graphene, carbon-based nano materials. That is electric double like conducting polymer metal oxides. The pseudo capacitor is due to the oxidation reduction, they produce extra charges and increase the value of capacitance. And from those materials, we can prepare the hybrid supercapacitor. Hybrid means we can then form a asymmetric pseudo EDLC or composite materials. If we make composite and we use composites for two electrodes, then that is the composite supercapacitor. Or asymmetric means one electrode is EDLC supercapacitor. Electrode material, current collector, and the electrolyte. Mainly, I will discuss here electrode material and the current collector part. The electrode materials is the core of the supercapacitors. It's directly govern the energy power characteristic of the supercapacitor. But the properties of this of the electrode materials that increase the contact point with the ion or electrolyte. Porosity also, if we increase the porosity itself, that surface area will increase. The porosity will enable the efficiency of the ion transport and facilitate the access. So if you can see contact between the electrode also increasing. And the surface functionalities, it enhance the wettability and can introduce beneficial for pseudo-capacitive materials, for the pseudo materials like oxide materials and the polymers. One material, that is the activated carbon. It has the high surface area and high porosity. From the ACM images, you can see these are the activated carbon. I will come to the point where how we can prepare this activated carbon, and they have the high porosity. So we generally prepare this activated carbon from the bio-waste global pollutant burning residues, fruit and vegetable peeling, and agricultural leftover like rice husk, bios, then like whatever we just throw those things produce the methane emission from the landfill. Even and what we do with the open burning that creates pollutants and soil water contaminations. So the problem is disposal cost what we can do, we can use those bio waste valuable material. So changing this bio waste to a valuable material, like we can prepare the activated carbon from this bio waste material. Like here we can see this is the bio waste material. These materials we can dry and then after some chemical treatment we can make the activated carbon. We have prepared like leachable biochar that is activated from biochar. We can prepare the activated carbon in different methods. First, we use this lychee peel and then dry it to make the powder. We can treat with acid or gas, and then some noise is okay. So from this lychee peel, we can make the powder and treat them with acid and then burn it, or we can burn it first and then treat with acid. The two methods we can do that, and then we can prepare the activated carbon material. Like here, the right side, we can see the AC images and the surface area. From BET, we can prepare the area just lychee peel biochar, means that from the lychee peel just burning this, we get the biochar, and what's the surface area is the 2.6 meter square, or for specific surface area is 2.6 meter square. After activation, the surface area increase and become 1,753 meters square per gram. So activated carbon has the really high surface area. So when we have this type of carbon materials, these are highly porous, conductive material. So we can prepare the supercapacitor using this activated carbon. Construct a supercapacitor like coin cell supercapacitor. Coin cell supercapacitor obviously will be flexible, but we need to characterize the material first. So we prepared the coin cell supercapacitor first. So we use two stainless steel coins. On top of those two coins, we deposit this activated carbon material, and we use a gel electrolyte in between two electrode, or some separator. We use the aqueous electrolyte, and this assemble work as a supercapacitor like the coin cell battery we use in our watch. So this material, and then from activated carbon we prepare from the lychee peel, it shows just biochar, it shows 12.24 farad per gram, whether after activation this shows 464 farad per gram. So huge increase due to this activation. There are I'm not going to show all those things. There are several materials or bio waste we have used, like lychee peel. Here this shows whether first thing is lychee peel activated with phosphoric acid and annual at 800 degrees Celsius shows good result of 464 farad per gram. And we also studied the on orange peel, that is Nagpur orange peel, that gives result like 479 farad per gram. Also, we have used marigold petals. Now we can ask why marigold petals, because we just after our function and puja, we throw these marigold petals here and there. So we try to check whether marigold petals will be useful for this activated material in supercapacitor. We found a really good capacitance value, 571 meter per farad per gram. And these different grasses, actually I forgot the scientific name, these different grasses we actually use to get the bioethanol, and they extract from that. After getting the bioethanol, we use activated carbon, and we found that it shows really moderate performance as
হুম,
supercapacitors.
হ্যাঁ, হ্যালো,
So we
হ্যাঁ,
can think about to use the biomass material to prepare
হ্যাঁ, হ্যাঁ,
activated
হ্যাঁ, ঠিক আছে,
carbon, and this activated carbon is not only
আচ্ছা,
for supercapacitor. This activated carbon, I think we know that activated
হ্যাঁ,
carbon is
হ্যাঁ, হ্যাঁ,
useful for
নিশ্চয় কেমন ডিফারেন্ট,
water treatment. That is for
বা
removal of heavy iron from
ওখানে
the
যদি ওরা বসে থাকে,
water, and also from
তাহলে ওদেরকে আর ট্রান্সফার না করে
organic
ওইখানে নিয়ে
effluent.
নিলেও হয়,
Also, you can
মানে জাস্ট
remove from water using
আমাদের প্রেজেন্সে নিতে
activated
হবে।
carbon. Okay, so this part is the activated carbon from
হ্যাঁ, যদি
biomass
প্রকাশদা যদি
material,
থাকে ওইখানে তাহলে
and I have
প্রকাশদা
shown
নিয়ে
you
নাও,
how to
প্রকাশদা যদি
construct a
সামনে আছে তো।
supercapacitor, a coin cell supercapacitor.
আচ্ছা, একবার দেখো তো,
Now,
যদি থাকে প্রকাশদা
the
যদি থাকে
other
তাহলে ওইখানে
material
নিয়ে নিতে হবে,
it's
মানে
interesting is
ওইখানেই হয়ে যাবে।
two-dimensional
হ্যাঁ, হ্যাঁ,
nanomaterial.
প্রকাশদাকে জিজ্ঞেস করুন, যেটা
Why
সুবিধা হবে।
these two-dimensional nanomaterials are important
ওকে,
for
আমি লিঙ্কটা
supercapacitors?
শেয়ার করে
Because
দেবো,
they have high surface,
ঠিক আছে।
specific surface area. They have extra electrochemical activities, helps to anchor the ions and all those things, and also it helps oxidation reductions and high mechanical flexibility. And 2D material possess confined thickness, which provides well-behaved electrical properties. So we use the activated carbon that can be used for EDLC, that is electric double layer capacitor. Dimensional nanomaterial can be different type of oxide materials can be used for pseudo-capacitance materials. Now, how we can prepare this type of 2D materials? There are several methods, but I'll show you here which we can easily, cost effectively prepare in our lab. There are solvothermal method, liquid phase exfoliation method, hydrothermal method, and reflux method. There are other methods also there, but these we can easily do in our lab cost effective method. So here I will show with example one by one. This is the liquid phase exfoliation of layered materials. So for two-dimensional nanomaterial, we should start with a layered material like transition metal oxides, transition metal dichalcogenides, or graphite types of layered material to get two-dimensional nanomaterials. Because each layer, if we get a layer by layer, we will get two-dimensional nanomaterials. So for example, if we start with graphite and try to exfoliate, we know the graphite is a layer material, and each layer is one with the van der Waals forces. There is no layers, but they have only the van der Waals forces. So if we can overcome, we can easily get a monolayer or bilayer graphene. So for that, what we have done is we for the different materials, it means it's optimizing the solvent is huge. So for graphite, suppose for example graphite, we can use NMP or DMF with some initial concentration of graphite in solvent. We disperse using sonication. There are some parameters like temperature, sonication frequency, and time. Optimizing those things, we can get some black dispersion of graphite, and to in that dispersion we'll have some few layer of graphene, monolayer of graphene, two layer of graphene, and also the graphite chunk. So to get rid of the only few layer graphene or monolayer graphene, what we have done generally we have to do is centrifugation. After centrifugation, we decant the top part, and what we get, this type of black dispersion. This is graphite. The graphite for graphite, you will get this type of black dispersion. So we don't know whether there is a graphene or just graphite or all this. So for that, we have to characterize this material to find whether these are graphene or graphite or monolayer, bilayer. We have to do several characterization. Under transmission electron microscope, you can see if it is graphene, you can see here this boundary, this is the graphene sheets falling here, and you can see it's the transparent. And aberration corrected TM, it shows the exact carbon hexagonal structure and the carbon position. You can see the carbon positions, and from white line scan you can determine the carbon bond length and the diagonal length. From this length, it shows that it's exactly for the graphene. So this must be graphene. And also we can do several other characteristics like Raman. We have to do some XRD and all those things. After that, we can confirm that this is graphene, and also the number of layer from Raman or TM. So this is the one method, the liquid phase exploration, and using the liquid phase exploration, we can prepare other layered materials like molybdenum oxides, two-dimensional nanomaterial, manganese oxides, ruthenium oxides. These materials are we can prepare using the liquid phase exfoliation. Not only the organic solvent, you can use water, but you need different type of surfactant for that. The other also we can prepare boron nitride, MOS2, tungsten sulfide, and we can see this type of materials. We can prepare two-dimensional nanomaterials using liquid phase exfoliation. Now the hydrothermal and sorbothermal method. It's the method is same. When we use water instead of solvent, other solvent, organic solvent, it called hydrothermal. Other than it called sorbothermal. Here, for example, we have tried to prepare, and actually we have prepared bismuth vanadate, which is also a layered material. We have prepared bismuth vanadate platelet structure of nanostructure. Start with some reagent in HNO3 solution, and then in mixer with other reagent, sodium vanadate. It depends what you are trying to prepare. So just mixing it, and then it seal it in a stainless steel hydrothermal reactor. And for different material, you need different temperature, different times, and for different structure, and then you will get some dispersion and centrifuge it, and you will get the your two-dimensional material. You can prepare different structure also, changing the parameters. So we can prepare like iron oxides, this type of iron oxides, and also the flower-like structure of bismuth oxychloride. We have prepared bismuth oxychloride, also a layer structure, and changing parameter. You can like see here, it's the flower-like structure. Also, you can make the composites. Flower-like structure, you can make the plate-like structure also, just changing the parameter. So when we have this type of material, we can make composites with carbon nanotube or activated carbon, and then prepare the supercapacitor. As I shown you, we can prepare the coin cell, right? We can prepare the coin cell and then can characterize these materials. But the thing is, this is the platelet structure of BiOCl. So platelet structure and the flower structure of BiOCl, just changing the parameter of temperature, time, nothing else. So we can get the different structure. So the thing is, the present technology is moving towards the flexible. That is the growing interest in the flexible electronics. So what we want to fold our TV screen and carry easily. We want to fold our phone and all those things. So our technology is moving towards flexible electronics. So what we need to do, each component of this device need to be flexible. So for similarly for energy storage device, we use here also need to make it flexible. So what we want a flexible supercapacitor. So we cannot make a coin cell supercapacitor. We need to make a flexible supercapacitor. So flexible supercapacitor means, so the supercapacitor component, there are three components. There are current collector, electrode material, and the separator. All three components need to be flexible. Not only flexible, we have to check whether due to the bending, the performance, what is the performance, whether degrading or it's stable. So to fabricate a flexible supercapacitors, we need a flexible freestanding films of active materials. Active materials means the electrode materials. Right? And also what we need are the supporting depositing activity material on flexible substrate. We can do those things. Either freestanding films of activity material, or we can deposit a thin film on a flexible substrate. So freestanding film we can prepare when we have the dispersion of nanomaterials. I have shown you how to prepare those type of nanomaterials. We can just easily make thin film. I'll show the procedure how to make thin film, and we can prepare this type of freestanding film. This is a graphene film. So this film is not only one graphene, it's a several graphene layer there. I mean, not layer, several graphene there to make this total film. To require the develop freestanding films of active materials. And the advantage of this, that if we can make up freestanding films, we don't need extra current collector. This will act both for as a current collector and also the electrode for the supercapacitor. Right. And it does not require conductive additives and binders. Thus the complete volume is used. Whatever the material here, all are used for the supercapacitor applications. When we have the dispersion, we can prepare in the lab scale. We can prepare the freestanding film using a vacuum filtration. Here's the vacuum filtration setup. We can change the thickness by changing the amount of dispersion we are filtering, and we get the film on top of filter paper. We can peel up and we can get this type of freestanding film. For example, we have prepared here vanadium phosphate. This vanadium phosphate I didn't show you here how to prepare. We have prepared using reflux method. So vanadium phosphate nanosheets here is the FEACM images, and this is the cross-sectional view of multi-wall carbon nanotube film. This multi-wall carbon nanotube film we have prepared using the vacuum filtration, and this is the composite film of multi-wall carbon nanotube and the VOPO4. This is the cross-sectional image of the freestanding film. When we have these films, we can use this as the electrode material for supercapacitor. Like this is this part as one upper electrode, lower electrode, and the separator in between. Separator we can, for aqueous, I said that for aqueous electrolyte we can use some membrane, filter membrane or something, or we can use the polymer gel without any other membrane, and then test it to know the performance of the supercapacitor. To know the performance of a supercapacitor, what we have to do is the cyclic voltammetry test. This is the CV test for the composite materials, multi-wall carbon nanotube and VOPO4 with different scan rate. Different scan rate means at what rate it's charging or discharging. You can see here 5 millivolt per second, means this is the charging rate. So for different charging rate, we get this type of current voltage characteristic. From here, we can calculate the capacitance value using the formula. And here is for comparison is shown that this red part is for multi-wall carbon nanotube film, and the blue part is the composite film. You can see the area under this blue curve is huge compared to the multi-wall carbon nanotube. So supercapacitors, the capacitance value for the composite is high. For specific capacitance, 236 farad per gram for the composite materials, and energy density here and the power density 147 watt per kg. Now this is the freestanding film for flexible devices. Other thing is the substrate supported flexible electrodes. So we know which type of electrode materials we can use. And those materials, when we have the dispersion of those materials, we can deposit on top of a flexible substrate. Like here, we use the doctor's blade method to deposit some active material on top of copper plate. This copper film actually is flexible. And then we can use this copper as current collector, and this is the active material. And here you can see the construction of this. It is the electrode material. Other side will be the copper, and this is the separator, and this is copper or aluminum foil, whatever we use. This is the construction of the supercapacitor. We can roll it and make a cell, like we can make like this or like this for future application. So we can transfer this to the industrial level, from lab scale to industrial scale. So the metal oxides, I'll show here now the different type of metal oxides which can be used as pseudo capacitor and which improve the capacitance value of the supercapacitor. Here we have prepared the metal oxides nanosheets and single-wall carbon nanotube composites, and prepared the thin film as I've shown, and transfer it on top of a flexible substrate. So here it is not a freestanding film. We will substrate on top of a flexible substrate. So it's a method to first we have deposited film on top of a particular type of filter membrane. We use here cellulose filter membrane, and then transfer it on top of gold coated PET. Here gold will act as a current collector. Gold coated PET. PET is the flexible substrate. Is in different this method on top of hot plate, and then so after depositing on top of gold, there is the activated material, and the above is the filter membrane. We'll while transferring, we'll make it the other side. The film side will be on top of gold. So this is the filter membrane, and this is the gold coated PET, and in between the activated material is there. Now we have to remove this filter membrane. Since we use cellulose membrane, we can easily dissolve it using acetone vapor at 60 degrees centigrade, and then what we get is the active material on top of gold coated PET. This is the one electrode. We can use same other electrode, and in between there will be electrolyte to make the supercapacitor. So this is the actual image. Single wall nanotube on top cellulose membrane. This is the single wall MO3 composite film on top of cellulose membrane. This MO3 was the 2-dimensional nanometer. I have shown you how the images previously. We used those type of materials, and this film was transferred on top of gold coated PET like this. Then we can make a sandwich, and then in between there will be electrolyte to form a supercapacitor. So this shows that a good flexible supercapacitor. We have checked the bending test, and we have seen that with bending there is no such change in the capacitance value. So this might be a good flexible supercapacitor. Okay, so another materials we have shown the performance. We will show the performance of the BIOCL multi-wall carbon nanotube composite based supercapacitor, flexible supercapacitor. We have prepared the same way, and it shows that with the different composition of the carbon nanotube and the BIOCL, different weight percentage, we have seen the 60% BIOCL is the best result with more than 400 Faraday-gram. And the bending test shows that this is the CV. There is no such change with bending, so it can be used as a flexible supercapacitor. So till now, we have seen which type of materials can be useful for preparing supercapacitor electrode. Like for electric double layer capacitor, we generally use carbon material like carbon nanotube or activated carbon or carbon black. And to improve the properties, we can use the pseudo capacitance material like molybdenum oxide, oxides materials, and they are nanostructure like 2-dimensional nanometer that I have shown you, and how to prepare a flexible supercapacitor on top of flexible substrate or a freestanding film. Now the thing is, our aim is to prepare a transparent, flexible supercapacitor. So till now, we came to know that this is how to prepare the flexible supercapacitor. Now these are not transparent, so these are not suitable for transparent flexible electronic devices. Right. For potential coupled as energy storage modules in various flexible, transparent, and portable electronics, what we need is a thin, transparent, conducting flexible film as a current collector. So there are three components: current collector, electrode material, and the electrolyte part. So all three components need to be transparent. So here we need a thin, transparent, conducting flexible film which can conduct current as well as we can see through it. That is the transparent. And active materials there also should be thin enough to be transparent. So first, we have to prepare a thin, transparent, conducting flexible film which can be used as a current collector. So till now, so for thin, transparent, conducting flexible films, conducting means the resistance will be very low with high transparency. So suppose for conducting material, like if we see the copper is a conducting material. It can conduct current, good conductor, but it's not transparent, right? So most of the transparent materials are insulator, but what we need a transparent conductor. And for thin film, the surface resistance and the transparency relation is like this, where sigma OP is the optical conductivity, sigma DC is the DC conductivity of the thin film, this is the Z0 is the free space impedance, and RS is the surface resistance of the film. If we plot this T versus RS, we will get like this type of curve. And from here we can calculate the sigma OP over sigma DC. As we increase sigma OP over sigma DC, the curve shifts towards left. And what we need is this region, that is low surface resistance, high transparency. For industrial purpose, mostly the target is more than 90% transmittance, but less than 100 ohm per square surface resistance. That is required sigma DC, sigma OP is. If we put here T and RS, you'll get what we need is 35, more than 35 sigma DC or sigma OP. So this is for transparent conducting film. So how to prepare this type of transparent conducting film? Till now we know that ITO or ZTO are suitable transparent current collector, but ITO, we all know ITO is used, you know. So the problem with ITO is it's ceramic in nature, so it's brittle, easily damage the film. I'll show how here it is showing the surface resistance with bending cycle for ITO. After 160 cycle, it just break. Surface resistance is with bending, the surface resistance increasing. Surface resistance increasing means conductivity is decreasing, and after 160 cycle, it just break. So this material ITO on top of some flexible substrate will not be suitable as a transparent conducting film for flexible devices. Also, the price is a factor. So what we can do, we have tried several nanomaterials, conducting nanomaterials to prepare thin transparent conducting films. But why we need thin transparent conducting film? That is for current collector of the supercapacitor in this case. Otherwise, we know for all display there are back electrode which is transparent conductor, and for flexible display we need a flexible transparent conductor. But here we'll use for fabricating or constructing a flexible transparent supercapacitor, and this one will use as a current collector. So nanostructure materials may be useful. So we have tried to test whether these nanostructural materials can be useful for making a transparent conducting thin film. So what we need, a thin film, a thin film of nanostructural material. There are different methods of deposition method. I have shown you how to deposit using vacuum filtering. There are other methods, is spray coating. We can do spray coating, spin coating, Langmuir block jet deposition, deep coating, wire coating. There are several other methods also there. So here for material characterization, we have mainly used vacuum filtration and also spray coating. So for vacuum filtration thin film, when we have dispersion, like for carbon nanotube dispersion, we have carbon nanotube dispersion. We So for carbon nanotube, you can see the RS versus T here. It gives sigma DCO 13. Here of 80 surface distance is more than 100. There's some problem. And for silver nanowire, it gives sigma DCO sigma P 500. That's good. But the problem is that required region, there is a deviation. There is some problem. And these are the evaporation method. This gives sigma P sigma PC 143. We cannot make thin film to get more than 40% oxidized. So this method not work. Silver nanowire thin film. So there is a problem. The thing is carbon nanotube is really conductive material like silver. I mean, not up to what we expect the good result, but there are some problem with carbon nanotube. Problem is when we deposit the carbon nanotube film on top of some filter membrane and transfer it onto PET, the carbon nanotube are cell junctions, carbon nanotube junction role. FMT, here is the carbon nanotube junction. This is one carbon nanotube, this is the junction, right? Here is the schematic diagram. We use the conduct AFM. So TP is conducting. We measure resistance using the IV, by IV using conducting AFM. Here you see the path here when we move the tip away, so the distance reach on the junction, there is a jump, a huge change in the resistance. And then if we move towards path 2, again like this, but this change is there. So there is a resistance. We move from here to cross the junction and then follow the path 1, it gives again it down and like this. So the problem is resistance. So to overcome this, we have tried other method to prepare the thin film using spray method and different carbon nanotube films, silver nanowire films. Here is the RS versus T for by spray method. Spray method we can change different like a schematic diagram of spraying system. We can change the pressure. We can change the speed of movement of these things. Here is the substrate. Here is the spray gun, and we can change several parameters like heating and all those things. We have prepared the film. We can see here is the above 90%, below 100 ohm per square. We got this type of film. Here I will show a film. Okay. So when we have those type of films on top of flexible substrate, we can check whether this can be used for flexible devices or not by electromechanical testing. Electromechanical testing means we'll use the electromechanical tester, modified it, and then what we did, bending cycle, we put a film here and then we just bend it, relax it, bend it, relax it. Like that, bending cycle for ITO coated PET, as I shown you before, it just break after 160 cycle. Whereas for carbon nanotube and silver nanowire, we can see these are for the silver nanowire carbon nanotube. If this is for the silver nanowire, you can see the bending cycle even after thousands, there is no such change in the resistance. That is, so this film can be useful for preparing some flexible devices if required. So yeah, here you can see this is a PET, on top of it there is a film. So this is converting film as and very there's no difference into our. So this is silver film on top of the transparent as well as. Okay. Now, when we have this type of transparent conducting film, that transparent conducting film can be used as a current collector for supercapacitor to make a transparent supercapacitor. We can make the thin active material, means like carbon nanotube or carbon and like oxide material composites, that active material we can make a very thin to make it transparent, and the transparent current collector total device will be transparent because you use generally polymer gel electrolyte which is also transparent. Here it is a bismuth oxybromide hydrothermal method. We have synthesized using hydrothermal method, and we have prepared a thin film of bismuth oxybromide on top of a conducting. Here we use carbon nanotube thin transparent as a current collector, and BIO-BR. This is the BIO-BR film, which is mostly transparent. This shows the transparency. Around 550, you can see we have prepared 80% transparency with different weight percentage, and we can use this to prepare a device of transparent supercapacitor. So to prepare a transparent supercapacitor, what we need? We need a transparent current collector. That I have shown how to prepare a transparent current collector. I have shown you which type of materials are good for supercapacitors. So using So here is a transparency capacitor. We have prepared 70% transparency with 907 microfarad per centimeter square. Here is not a farad per gram or something. Since it's transparent, we use per unit area. 97 microfarad is a huge capacitance. Okay, even after flexing and bending, you can see there is no such change in the capacitance value. Okay, so we can use our machine learning or AI to find the or tune the which type of materials will be useful for supercapacitor electrode. We can optimize, but before that, you need to know previous results. So I've shown some results, and you can go through other papers. And then, if anyone interested, you can go through use the AI and ML to find and optimize the find the materials, suitable materials, and get the good performance of supercapacitor. So the prospective applications of supercapacitors: solar supercapacitor charging station in the garden or parking. We can use a supercapacitor which gives instant power. So if you have solar cell, from there you can take power, and through supercapacitor there will be charging. Why supercapacitor? Through because it gives instant power, quick power, and huge power. We can integrate solar supercapacitor group, means it will act as a solar cell as well as the supercapacitor. And here, we use the battery when we start the car. It gives a high pressure, and it affects on the battery, right? So if we use a supercapacitor after battery and supercapacitor just combine, then the power required will come directly from the supercapacitor. When we stop the car in our signal, the supercapacitor will be charged immediately, and then when we start it, the supercapacitor will give the power, not the battery. So in this way, hybrid electric vehicle, in this way we can increase the lifetime of the battery as well as the car. I think for implantable healthcare, portable devices, all type of portable devices, we can use the supercapacitor. How we can use the supercapacitor? We can integrate the nano generator with supercapacitor. That nano generator will produce the energy, and supercapacitor will give the constant power to the devices. Nano generator cannot give constant power because it fluctuates. So supercapacitor will give the constant power to the implanted devices. To develop self-sustainable power supplying units for large applications such as lung motion through breathing can generate up to 1 watt of power, which is sufficient to drive the pacemaker. So if we integrate the nano generator, a small nano generator, and the supercapacitor, that lung motion can produce huge power, which can be used for implanted devices. Another thing is impact from heel strike when we walk. The impact of heel striking the ground when walking is particularly rich source of energy, with 67 watt of power available from brisk walker. Is for average walking. Harvesting or storing up 1 to 5% of this, and using the supercapacitor, we can it will be sufficient to run many body on multimedia devices. Okay, so to know more about this work, you can go. Okay, these are the. Okay, so thank you. If you have any questions, you can ask me. Okay, so is there any discussion you want, or if you want any question, or if you have any suggestion?
Professor De, is it done?
Yeah, it's done. Just I'm waiting if anyone has suggestion or any question.
Okay, so the basically session is open for question and answer.
Yeah.
So the participant, you are requested to put forward. You have any question? Dr. Mondal, Subhrata Mondal.
Yes, Bhushan. Yes, sir.
Yes, do you have any question?
Actually, in that topic selected, presented is nice, very nice, and I think that should be more relevant in the AIML regarding.
Okay, so the basically application of AI/ML in supercapacitor or any energy storage.
Yes. You can use when you have knowledge. Since you have knowledge on AI and ML, you can use to optimize the properties. Which materials will be suitable for supercapacitor that you can study, and you can focus the performance of the supercapacitor as well.
Okay, so basically, Professor Day has outline of this supercapacitor and the details of working principle, details of the material used, and what are the metals that can be used. So with this knowledge, probably if anybody is interested to have the application of AI/ML in this field, so he or she can do.
Yes.
So fine. So any question from any other participant, please? Back with Daro. Okay, so if there is
Sir,
no
what is the band gap
yeah.
generally required for these high active supercapacitors?
Okay. So listen, the thing is for electrode materials, you need a good conductive material, right? So if you have high band gap material, then there will be a problem. The thing is for pseudo material, like oxides materials used, they have band gap like around 3 electron volt, 3.4, 3.5. Even you can go higher, there is no problem. But that's for pseudo capacitance material, the conducting part we are not using. They are, due to their oxidation and reduction, we are getting extra charge. But only that pseudo material which has the high band gap cannot be a good choice for electron material. We have to make composites with good conducting material like carbon nanotube or active material. So making composites with carbon nanotube or activated carbon with those transition metal oxides or chalcogenides will be good, because activated carbon itself will perform well, as well as the oxidation and reduction of those oxides materials will provide extra charge.
So composites mean heterostructure or just physical mixture?
You can do both way, heterostructure or mixed, just mixing those things. But if you do mixing, you need to be a homogeneous mixing. Otherwise, there will be a problem.
Okay, sir. Thank you very much.
Welcome.
Okay, so any other question?